Hi everybody, welcome back to Calc 2 by Example. Today we're going to start the last section, which is on power series. Alright, so remember that for us in this class, we're going to sort of think of power series as infinitely long polynomials. Okay. So in this question, we're asked to find the interval of absolute convergence for a power series. And we're actually going to use one of our series tests for this. So this is a power series. You could think of it as an infinitely long polynomial. There are variables, there are coefficients, there are exponents. You're not dividing by any powers of x though, which is why I say we're sort of thinking of it as an infinitely long polynomial. So how are we going to do this? Well, we're going to use the ratio test, okay? And frequently for this sort of problem, you're going to either want to use the ratio test or the root test. All right, so the ratio test says we want to look at the n plus first term divided by the nth term. And because I'm asked for absolute convergence, I take the absolute values of those. So the n plus first term, well, if I replace I with n plus 1, we get a term that looks like this. And I want to divide that by the nth term, which is the same as multiplying by its reciprocal. So if I took I and I replaced it with n, I get an expression that looks like this. And it's upside down because dividing is the same as you flipping and multiplying, okay? All right, so this is the expression that I need to deal with, and the first thing I'm going to want to do is sort of cancel as much stuff as I possibly can, all right? So going from this line to this line, you'll see that I lost a whole bunch of copies of 2. So I had n plus 1 copies of 2 here and n copies of 2 here, so I'm just left with 1 extra copy of 2. Because when you divide like bases, you subtract exponents. And the same thing happened with the quantity x minus 3. I had n plus 1 copies of x minus 3 in the numerator, n copies in the denominator. You cancel out all but one of the copies in the numerator, and so we're just left with a single copy of x minus 3. The n squared plus 1 and the n plus 1 quantity squared plus 1 don't go anywhere, but that's okay because we're going to sort of take care of those with the limit. Okay. Now, as we take the limit as n goes to infinity, the 2 and the x minus 3 don't go anywhere because there aren't any n's. And if we look at this rational expression, I have a quadratic divided by another quadratic, and so the limit is just going to be the ratio of their leading coefficients. So in this case, that'll be 1 divided by 1, and that's 1. All right. So when I take the limit as n goes to infinity, I'm just left with 2 times the absolute value of x minus 3. For this series to converge using the ratio test, I need that to be less than 1. Okay? So the reason I'm saying that I want this less than 1 is because that's how the ratio test works. And if you forgot about how the ratio test works, you should go back and check out the other video in this series where we do an example of that when we're doing convergence tests. Okay, so if this has to be less than 1, I can now solve that inequality. And in solving that inequality, I get that the radius of convergence, the distance from the center to sort of the outer edges of the interval, is 1/2, and that the interval of absolute convergence goes from 5 halves to 7 halves. In case you've forgotten, the center in this case is 3 because we have a polynomial where we have a whole bunch of x minus 3's. Okay. Another way of viewing that is that if you solve this inequality for x, 3 is right in the middle of that interval, and so 3 is the center of the power series in this case because it's in the middle of the interval of convergence. Okay. Which isn't a great technical way of thinking about it, but it's a good way to visualize. It's a good way to remember it and understand it. All right, so that's calculating a radius of convergence for a power series. This sort of assumes, though, that you already have the power series. So in the next video, what we're going to do is we're going to look at one of the places these power series can come from by looking at linear approximations and polynomial approximations of functions that will eventually lead to representing functions using power series. I'll see you there. I'll see you later for that.